Okay, in this video we're doing problem set 68 from Calc AB. Problems and playlist are in the description below, and let's see what the questions say. Write down the antiderivatives you have memorized, so like trig, arctrig, exponential, power rule, inverse and arctrig, same thing. I just wrote out ahead of time the ones that we're going to need to do. So we're going to do the antiderivative of x to the n, that's reversing the power rule, so we know that's going to be plus 1 times the reciprocal. 1 over n plus 1 times x to the n plus 1 plus c. There's when you're formally writing it, you would say n is not equal to negative 1, because if n is equal to negative 1, then you're actually integrating 1 over x, and we know that 1 over x has a different antiderivative. So I don't remember if I went to 1 over x or if I went to e to the x next. I'm going to assume that I went to 1 over x because that would make sense, but there's no guarantee. The antiderivative of 1 over x dx, we know, is the natural log of the absolute value of x plus c. So we need absolute value there so that the domain of the antiderivative is the same as the domain of the derivative. If you just have 1 over x, the domain is everything except for 0. So we can't say the antiderivative is just natural log of x because that domain is only greater than 0. Throw in the absolute value and you matched up the domains. So that's what we do there. Integral of e to the x is e to the x plus c. And then the integral of a to the x, this is one, there's a couple where if you don't have them memorized, you're you're really in the weeds, you're stuck. A to the x, the derivative of a to the x is a to the x natural log of a, so the antiderivative is going to be 1 over natural log of a to the x plus c. Cosine is going to give us sine plus c. Sine is going to give us negative cosine. So if you get a co-function in the antiderivative, you're going to have to multiply in a factor of negative 1. And you'll see that over and over. Secant tan is another one. If you don't recognize it, you're probably going to be in a little bit of trouble. Secant tan is the derivative of secant, so the antiderivative of secant tan is secant. Cosecant cotan, so we have a co thing going on. We're going to get negative cosecant plus c. Secant squared is the derivative of tangent, so the antiderivative of secant squared is going to be tangent. And that's how I do it in my mind. I always think this is the derivative of what? I do that for all the trig functions. I basically have the derivatives memorized, and then I run through that list and work backwards. So if you know the derivative of tangent is secant squared, then you know the derivative of cotangent is negative cosecant squared. So the antiderivative of cosecant squared is negative cotangent. And then these last two are going to be our inverse trig functions. 1 over the square root of 1 minus x squared, that's going to be arcsine, or inverse sine, however you want to say it, plus c. And then 1 over 1 plus x squared. So if you see 1 over x squared plus 1, I would encourage you to rewrite it as 1 over 1 plus x squared. There's a lot of benefits going forward to thinking of it in terms of that. So that's what I always do. 1 over 1 plus x squared is arctan. And those are the ones that you need to have memorized to be able to fluidly move through problems. All right, let's look at another thing. Given that a of t is 6t plus 1, v of 0 is 4, s of 0 is 5, we just want to find s of t. Not bad, we've done a bunch like this. So to go from acceleration to velocity, we need to find antiderivative. And in this case, polynomial, so we're just reversing the power rule. So I'm going to say that v of t is 6 times 1/2, which is 3t squared. And then the antiderivative of 1 is going to be t, but we pick up a plus c. And then to solve for c, we're going to use this fact. So we know that 4 is basically equal to c because the 0 that you plug in just zeroes everything else out. So our velocity is really 3t squared plus t plus 4. To go from velocity to position, you find an antiderivative. So again, we're reversing the power rule. So we're going to end up with s of t is 3 times 1/3, so just 1 times t cubed. And then t to the first plus 1 times the reciprocal, 1/2 t squared, 4t plus c. Again, we want to solve for c by using s of 0 is 5, which again zeroes everything out, and we just get c is equal to 5 in this case. So our final answer for s of t is t cubed plus 1/2 t squared plus 4t plus 5. Let's take a look at one more question, which has 2 parts, so that's okay. This is part of why you want to memorize your antiderivatives. I look at this first one, part A here, 1 over 1 plus something squared. 1 over 1 plus something squared, to me, kind of screams arctan. So I'm thinking this is the derivative of arctan of something. So it should be 1 over 1 plus something squared. 4x squared is something squared. That thing would be 2x. So I think we're looking at u equals 2x here, which means 1/2 du is equal to dx. We make all of our substitutions. We're going to get the 1/2 that we'll just pull out, 1 over 1 plus u squared du. Perfect. That's 1/2 arctan of u. And then when we substitute for u, because remember the original doesn't have u in it, we like introduce that concept. Substitute back in, 1/2 arctan of 2x plus c. That's a pretty good problem. You got to recognize the arctan and then do a u substitution. Not bad. All right, for the next one, since we just did an arctan, I'm immediately thinking this is probably arctan. When you have a quadratic in the denominator, you can try to make the whole quadratic equal to u, and then maybe it's going to be like a natural log or just reversing the power rule. Like that's something that can happen. When that doesn't happen, you should think to yourself, arctan has a quadratic in the denominator, its derivative rather. So, right, 1 plus u squared is a quadratic. So we have a quadratic here. Maybe if we can make this look like 1 plus u squared, we'll be able to integrate this somehow. So the way we're going to do that is complete the square. So there's a couple of algebraic techniques that you definitely need to know for AP calculus at least. One of them is polynomial division, which we're not doing here, but ultimately we'll do some of those. So polynomial division and completing the square, both of those are really important in terms of doing like, I don't know, the most algebraically complicated antiderivatives that you'll run into, I guess. So we need to complete the square. I look at x squared minus 4x and I think to myself, x squared minus 4x plus 4 is definitely a perfect square. So I have videos on how to complete the square if you don't remember, but you can often do them this way. X squared minus 4x plus 4 is a perfect square. That's the quantity x minus 2 squared. So I'm going to take that 5 and divide it into 4 plus 1. So I'm going to rewrite this thing as 1 over x squared minus 4x plus 4 plus 1. And then I can factor that. 1 over the quantity x minus 2 squared plus 1. Now I can do a u substitution. So I'll let u equal x minus 2. This is the best kind of substitution because du is just dx. Never forget, you have to substitute for dx. Sometimes du is dx, but not always. Make all of our substitutions and rewrite it so it looks like the way we have it memorized. We're doing the integral of 1 over 1 plus u squared. We know that's arctan of u for sure. And we know that u is x minus 2 because we have that step where we wrote u equals x minus 2. So our final answer is arctan of x minus 2 plus c. That's the whole problem set. I hope you found this helpful and good luck.